Logistic differential equations. Before we start talking about logistic growth, let's talk about exponential growth. This is typically a topic that is covered in pre-calculus and is also used to help understand population models in pre-calculus. But if we try to really think about what this means in terms of a population growing, exponential growth would be an unsustainable model for the limited resources that we have in any type of population. So just thinking about the human population, if this red curve here modeled human population growth, if it is increasing at this rate, then we would not be able to sustain that type of growth. So exponential growth is not actually a very good way to model populations. The corresponding differential equation that corresponds to a solution that looks like exponential growth has this form. So dy dt equals k times y, where k is some constant. If I were to solve this differential equation to find a general solution, so y equals, it would have this general shape of an exponential growth function. So just to kind of show what that looks like, this is a separable differential equation. So I can go ahead and divide by the y, so I get dy over y, and then I'll have k dt, where k is some constant. So the antiderivative on the left is going to be natural log of the absolute value of y, and the antiderivative on the right, since the variable is t, is going to be kt plus c. So now here, if I wanted to solve for y, I would have to exponentiate both sides. So the absolute value of y is e to the kt plus c. And of course, it's going to end up being either plus or minus, but we don't have an initial condition. But the bottom line is that the answer is going to be an exponential function of some form. So maybe a shift or a stretch, but it's going to have the same general shape. So a differential equation of this form will give us a solution of this form, so on the left of this exponential growth, but neither of them is a good example of what population should be modeled by. So population cannot grow at this rate, so the differential equation that corresponds to it represents the rate at which population grows. So this is not a function that we would want to study to help us look at some realistic population models, not just for humans, but of all kinds of species. So we're not going to use exponential functions to model population growth. We're going to look at logistic growth functions. So logistic growth functions have this general shape. So this is an example of a logistic growth function, this blue curve. So this would be the solution to a particular type of differential equation that we'll take a look at in a second. And if you'll notice, this too is an increasing function everywhere, the way that it is currently drawn. But it doesn't quite grow as quickly as our exponential growth function. And we have some special terms labeled here. So y sub 0 is considered our initial value for a logistic growth function. So that's going to be like our initial condition. And we have this value here, y equals L, which you'll notice is drawn as a horizontal line. And that has a special name called the carrying capacity. So since we're going to be talking about population models, the carrying capacity is going to be what's that maximum population that we can possibly sustain with the resources that we have. So we never quite want to hit our carrying capacity. We would just at most want to approach it, because then we would run out of resources. So L, that number, is like the maximum population we would ever want. But again, we don't ever want to cross it or get to it. We would want to approach it so that we don't ever, in fact, run out of resources. So the idea of approaching in math, we should be thinking a horizontal asymptote here. So a horizontal asymptote of a logistic growth function, that numerical value that is the answer to that horizontal asymptote, or that limit at infinity, since we're talking calculus, is the carrying capacity in a population model. And then there's another special value labeled here. It's half of the carrying capacity. So at y equals L over 2, so this point here on the solution curve is the place where the population increases most rapidly. So it's going to be the steepest slope at any point on this curve. So this is going to be an important value for us, and I also want you to notice in looking at this curve that it's the point of inflection. So from this initial value to this half the carrying capacity location, I have a concave up function, and this is where I change to a concave down function for the rest of the logistic curve. So this is considered an inflection point on my logistic growth function. So these are all these are the important things that we need to know going into the formulas we're going to now take a look at for logistic growth functions and their corresponding differential equations. Now let's take a look at the formulas that correspond to logistic differential equations. So a logistic differential equation has the form dy dt equals k times y times the quantity 1 minus y over L. So I want to stop and take a look at the fact that it's similar to an exponential growth function in this first part here. So dy dt equals k times y was a differential equation that had a solution that was an exponential function. But now adding this quantity that we multiply by, 1 minus y over L, that's what makes the solution a logistic equation. So when the logistic differential equation is written in this form, by looking at it, we can find a few things regarding the solution curve and about the population that it models. So k is considered to be the growth constant, so k being this number in front multiplied by y. And capital L, as we looked at the corresponding graph, we said capital L was the carrying capacity. So that was the maximum population size an environment can sustain. So if the differential equation's in this form, the number that's being divided into y is my carrying capacity. And then again, back to the curve that we looked at, half the carrying capacity, so L over 2, is the population when the rate of population is increasing most rapidly. So on the graph, that corresponds to the place with the steepest slope, and that's the maximum growth rate. So if we think about tangent lines, where I'm going to have that slope with this, the line with the steepest slope, that output, so that was along the vertical axis, that's going to be L over 2. That's going to be the population when the population is growing the fastest. But this is not a time. So a lot of people get that confused. So if L is an amount of species, L over 2 is still an amount of species. So it's not a time, it's an amount of whatever we're quantifying. But if I look at the input to whatever L over 2 came out of, that would then be a time. So the vertical axis is in a number of species or quantity that we're counting, but the input is the time. Now, if I have a logistic differential equation of this form, this is separable. So I can solve this. However, it would require an integration by parts, which I know is not your favorite thing. So because this does come up so often, and because we can transform these differential equations to look like this format, there's a general solution formula. Now, it too is a little bit messy, but not as bad as doing an integration by parts every time. So the solution is y equals L, the carrying capacity, divided by 1 minus c times e to the negative kt. So k is that growth constant, and c we actually need to find. So c is the initial value minus the carrying capacity over the initial value. So the solution itself does take a little bit of effort to memorize, as does trying to memorize the form that we want our logistic differential equation to be in. But once we start to recognize this and apply it, it's going to become a lot easier than attempting to solve this as integration by parts problem. The general shape of a logistic function depends on the initial value, so let's take a look at those different cases. Let's assume that the initial value is between 0 and L over 2. So remember, L is the carrying capacity. So my initial value is somewhere between 0 and half the carrying capacity. So here on this graph, here's an example of my initial value occurring sometime between 0 and that L over 2 value. And the general shape is going to look like the previous logistic curve that we had taken a look at earlier, that started out concave up and then reached its maximum rate and then turned into a concave down function. So we have this inflection point happening here. And that's only because my initial value is between 0 and L over 2. So what we can think about is that the population is starting out at whatever this value is, and it hasn't reached its maximum growth rate yet. But then once it does, it starts to level out and it starts to approach its carrying capacity. So that means that as t approaches infinity, the limit of y of t is going to equal L, which is the carrying capacity. So this is another way of saying that L is a horizontal asymptote of the function y of t. So this is one possibility. It's specifically the case when the initial value, the initial population, is between 0 and half of the carrying capacity. The other two possibilities is if the initial population is between the half of the carrying capacity and the carrying capacity. So in other words, it's between L over 2 and L. And then the graph would just look like the concave down portion that is approaching the carrying capacity. And the final option is if the initial population is greater than the carrying capacity. So this one's the one that looks significantly different, and we should try to think about it in the sense that if there's already more than the population can handle, then that must mean that we're going to end up approaching the carrying capacity in a decreasing fashion. So now I have a decreasing function that's approaching the carrying capacity, and in both cases, the limit at infinity, as t approaches infinity, is L, the carrying capacity. So I should really say in all three cases, as t approaches infinity. So as time goes on, all of the populations, no matter where they started, are going to end up approaching the carrying capacity. Before we start solving problems, here are the types of questions that we could be asked involving logistic growth. So the first one we could be asked is find the carrying capacity. We could be asked, when is the population growing the fastest? And what is the population size when the population is growing the fastest? Find all horizontal asymptotes of a logistic growth equation. And this could also be asked in the form of limits at infinity. We could be asked to find the population function, or population at a certain time given p prime of t, or given a differential equation. So we can solve the differential equation, but in most cases we just want to apply that formula instead of doing an integration by parts. And then we can be asked, where is the solution curve increasing, decreasing, and find a point of inflection on a particular solution curve. So this is the range of questions that we could be asked involving logistic growth. Now let's solve our first logistic differential equation. So solve dy dt equals 0.3y times the quantity 4 minus y with initial condition y of 0 equals 1. So until we get used to the formulas, let's go ahead and write them off to the side so we can see what we're aiming for. So we want our differential equation to look like ky times 1 minus y over L, so that we can find our constant and we can find our carrying capacity. So this doesn't quite look like the form that we need it. The problem currently lies within the parentheses, so we're going to want 1 minus y over L. So in order to turn this 4 into a 1, I'm going to need to factor out a 4. So let's go ahead and rewrite this. I'm going to rewrite this as 3/10, so 0.3 is 3/10 y, and I'm going to go ahead and factor out the 4. So if I factor out a 4, what's left inside the parentheses is the 1 that I need. But if I factor a 4 out of y, it's really like I'm dividing by 4. So we should be able to think about, if I substitute or multiply the 4 back in, distribute 4 back in, 4 times 1 is 4, and 4 times y over 4, the 4's would cancel and give me y. So pulling out the 4 leaves me with an expression inside the parentheses of the form I need it to be in. But that's going to affect my k value in front. So this is like 12 over 10, which simplifies to 6 over 5y, 1 minus y over 4. So this is my logistic differential equation in the proper format I need it to be to find my k value. So here's my k value, and to find my carrying capacity L. And now we substitute into our formula for the solution curve. So our formula is going to be y equals L over 1 minus CE to the negative KT. Where C has its own formula, it's the initial condition minus L over the initial condition. So now we're going to try to find the solutions by substituting in the quantities that we know. So y is going to be L, my carrying capacity, so 4 over 1 minus, I'm going to leave a space here for C because I'm going to need to solve for C, e to the negative 6 over 5 t. So 6 over 5 was my k value, but the formula called for negative k and then times t. So now to find the c value here, I'm going to need to substitute in the information regarding my initial condition. So remember, this also translates to y sub 0 equals 1. So this would be 1 minus my carrying capacity 4 over 1. So my c value is then negative 3. So since I'm subtracting a negative, it will turn into plus positive 3. So my solution is 4 over 1 plus 3e to the negative 6 over 5t. And that is my solution. So it did take a little bit of effort to rewrite the differential equation, and it would take some effort to memorize these formulas, but not nearly as much as solving the integral that would require an integration by parts when solving this separable differential equation. Let's take a look at another problem. We want to suppose that a population develops according to the logistic differential equation dp dt equals 0.2p minus 2/1000 p squared, and t is measured in weeks. So let's take a look at what we're being asked to solve. If p of 0 equals 5, so if the initial population is 5, what is the limit as t approaches infinity of p of t? And then we're being asked to evaluate that same limit, but with different initial populations. So if the initial population is 60, if the initial population is 120. And hopefully what you're thinking, what you remember, is that it doesn't matter what the initial condition is. These are all going to be the same answer. They're all going to be the carrying capacity. It doesn't matter where we started. The solution is always going to approach the carrying capacity. So we need to rewrite our logistic differential equation in a form where we can easily identify that carrying capacity. Now, we were given that initial formula in terms of y. So we had dy dt, but I've gone ahead and rewritten it with the variable p now. So we want dp dt, so it's going to be k times p is what we're looking for. So instead of k times y, and then 1 minus p over L instead of y over L. And then if we were interested in a solution, then the solution would be called p instead of y. And that's going to be the same formula, L over 1 minus CE to the negative KT. And C is the same, defined the same way as well. So let's go ahead and try to rewrite this so that it looks like it's in this form. So here, what I'm going to do is start out by writing these as fractions. So if you feel like you're good with manipulating decimals, that's fine too. We're ultimately going to pull out 0.2p because we want to end up with that 1 inside my expression in parentheses. But I'm going to rewrite this as, that's 2/10, 0.2 is 2/10, so 2/10 p, and then minus, this is 2/1000, so 2 over 1,000, p squared. And then maybe it is, maybe it isn't, a little easier to see. We're going to pull out 2 over 10p from this first term. In other words, we're going to be left with 1. And then minus, if I pull out a 2 over 10 from here, if I pull out a 2 on the top, I'm going to have a 1. And if I pull out 10 on the bottom, I'm going to have 100. So on the bottom, if I have 100, and then notice I also pulled out a p, so I'm going to have 1 copy of p left on the top. So now this is in the form that I wanted it to be, so I can easily find my carrying capacity, which is 100. So we can think about distributing it back in and everything would work out correctly to get the original equation that we were given, or the original expression we were given. But now it's just easier to see the carrying capacity is 100. But again, it doesn't matter for parts A, B, and C that the initial population was 5 and then 60 and 120. The answer to A, B, and C are all 100. Towards the end of time, if there's not really any other way to say this, as we start approaching infinity, if time starts moving on, we're always going to approach our carrying capacity on the population function itself, on the solution curve to this differential equation. Where these matter is for part D. So sketch the solution curves for A, B, and C. Which one has an inflection point? So if the initial population is 5, let's just do a little sketch for A here. So what we know is that 100 is my horizontal asymptote because this limit at infinity is 100. And L over 2, 100 over 2 is 50. That's where my change in concavity is going to occur. And I started out at time 0, so here's my t-axis, here's my p of t-axis. So at time 0, I'll do the graph in a different color. At time 0, my population is 5, and I know that it's going to change. It's going to have a steepest slope here at an output value of 50. So I'll go ahead and draw a function that's increasing concave up and then switches to increasing concave down where I approach my carrying capacity. So this is a sketch of what the solution curve to A will look like where I'm starting out at 5. And so my steepest slope should be occurring right here at L of 2. So when the population is 50, because remember this isn't a time, so I don't want to say at time 50, it's at time whatever this value is at this t1. So which one has an inflection point? A. This graph has an inflection point right there at the L over 2 location. And now if we were to do a sketch of B and C, so B has my initial population occurring between L over 2 and L. So if this is 100 again, which still remains my horizontal asymptote, my carrying capacity, here is 50 L over 2. So now if I start out with a population of 60, now my graph is just going to look like this, where I'm approaching this horizontal asymptote at 100, so no inflection point there. And then for part C, now I have this population that can't be sustained to begin with. So I have this population that is 120, and I can only sustain 100, so that means my graph is going to have to be decreasing to approach what I can sustain, the carrying capacity of 100. So also no inflection point. For another example, we have the population P of t of a species satisfies the logistic differential equation dp dt equals P times the quantity 2 minus P over 5,000, where the initial population is 3,000 and t is given in years. What is the limit as t approaches infinity of P of t? So in this case, again, we are going to need the carrying capacity. So as t approaches positive infinity, what's going to happen to this population? Well, it's going to approach the carrying capacity, which at this point, because it looks so similar, a lot of students might just go ahead and say 5,000, but it is not quite in the correct form yet. I need to have a 1 where this 2 is. So in other words, I need to pull a 2 out of this expression inside parentheses. So I am going to have 2p times 1 minus p over. So if I pull out a 2, it's like dividing by 2. So this 5,000 becomes 10,000. And again, if I need to double check, I can always think about distributing the 2 back in. So I'd get 2 over 10,000, which in half is my 5,000. So this does work out. So this limit as t approaches infinity of P of t is the carrying capacity 10,000. Alright, in this next problem, what are all the horizontal asymptotes of all the solutions to dy dt equals y times the quantity 8 minus y over 1,000? So just when you think you've got this concept down, I'm throwing a little bit of a curveball at you. So the question's asking us to find all the horizontal asymptotes. to this general logistic differential equation. So we're not told that this represents a population. This is just a differential equation, dy dt. And to find horizontal asymptotes of the solution, so let's remind ourselves solutions are of the form y equals. All horizontal asymptotes mean that we want to know what happens as t approaches infinity of y of t. And this is the one that we've been solving a few times in a row now. But to find all horizontal asymptotes, we also have to think about what happens as t approaches negative infinity. So if this were a population model, this whole idea of t might stand for time, but right now t is just a variable. So we are going to consider what happens when t values approach negative infinity. So we're not thinking of t as time right now, just as the other variable involved in this differential equation. So to find the horizontal asymptote that corresponds to t values approaching positive infinity, we just need the carrying capacity. So we can go ahead and turn this into the right form where this value is a 1, so we'll factor out our 8. So 8y is going to be 1 minus y over 8,000. So what's in the position of my L, or my carrying capacity if this was a population problem, is 8,000. Now 8,000 is the solution to this limit at infinity, but the answer to this problem has the form of a horizontal line. A horizontal asymptote has to be written as y equals that particular number. So this is one solution. And now we have to try to think about the other solution and maybe even think about where this number comes from. So we want to know the horizontal asymptotes of all the solutions. So why don't we go ahead and write out the solution to this differential equation. So my general formula is going to be L. So L is 8,000 over 1 minus C, and I'm going to leave C there, and I'll talk about why in a second, e to the negative 8, my k value, 8t. So I have to leave C there because C is defined to be the initial population or the initial condition minus L over y0, and I don't have a y0. I wasn't told anything about a specific solution. Plus, I want the horizontal asymptotes for all the solutions. So the general solution looks like 8,000 over 1 minus CE to the negative 8t. And I want to evaluate what's happening as t approaches negative infinity. So the limit as t approaches negative infinity of 8,000 over 1 minus CE to the negative 8t. So here's what we're thinking about is plugging in really big negative numbers, or really negative numbers, into this t value. So if we think about plugging in large negative numbers here, well, a negative times this negative 8 is going to give me a positive. So if I take e and raise it to a positive big number, the denominator, or this portion right here, let me try to highlight it, this whole portion here is going to be some huge number. And then I'm going to have 1 minus that huge number, so the bottom is going to be really big, but negative, because I'm going to have 1 minus, a billion, a trillion, so I'm going to have some really big negative number. And the top is constant. The top is 8,000. So if I have a constant, but the bottom's growing really big, let's remember limits, it's been a while now, but this whole thing is going to go to 0. So that means that the solution to this second limit at infinity that is needed to find all horizontal asymptotes, solving both of these limits, is going to give me 0. So y equals 0 and y equals 8,000 are my solutions. And real quick, let's just take a quick second to think about where 8,000 comes from. Imagine now if I'm solving the positive infinity version. So now this portion right here, CE to the negative 8t, well, if I plug in big positive numbers, it's like C over E to the 8t. And if I have to plug in positive values, this is a negative, it'd go to the bottom. So that means this portion here would go to 0. Sorry, I got kind of sloppy. But if I'm plugging in positive big numbers, this whole portion will go to 0, which is going to be 8,000 over 1. Or the top is always just L. So it's always just the carrying capacity. So that's where that comes from, is finding the limit as t approaches infinity of the general solution. Moving on to another type of question, we're going to suppose P of t denotes the size of an animal population at time t, and its growth is described by the differential equation dp dt equals 2/1000 p times the quantity 1000 minus p. How many animals are in the population when the population is growing fastest? So this key phrase here, when the population is growing fastest, it corresponds to the time when the population is at L over 2, so half the carrying capacity. So we are going to need to know the carrying capacity here so that we can divide it by 2, because that is the population when the population is growing the fastest. That's that inflection point value, the output of that inflection point value that we're looking for. So we're going to need to rewrite this so that it's in the correct form to find the carrying capacity. So dp dt is going to equal, so I need a 1 right here where I have a 1000. So I'm going to need to pull out 1000, and if I multiply 1000 by 2/1000, I'm going to end up with just a 2 in the front as my growth constant times p, and then I pulled out 1000, so I'm going to have the 1 I want minus p over 1000. So that means that L, my carrying capacity is 1000. So the population is growing fastest when the population carrying capacity is cut in half. So the answer here is L over 2. So L is 1000, and L over 2 is then going to be 1000 divided by 2. So 500 animals is the answer to how many animals are in the population when the population is growing fastest. Now we take a look at a problem that has a few different parts to it that kind of wraps everything together. The rate at which the flu spreads through a community is modeled by the logistic differential equation dp dt equals 1/1000 p times 3000 minus p, where t is measured in days. Part A. If p of 0 equals 50, solve for p as a function of t. So for part A, we're being asked to solve the differential equation with initial condition at time 0, 50 people have the flu. So we're going to need to rewrite this differential equation in the form that's going to allow us to easily find a solution with a given initial condition. So over here, I'm going to rewrite dp dt equals, I'm going to pull the 3000 out. So 3000 times 1000th is going to give us 3. So this is 3p times 1 minus p over 3000. So that means that 3000 is my carrying capacity and 3 is my growth constant. So for part A, I'm going to need my formula for y, or actually I'm not going to call it y, I should call it t, so there's no y here. So I'm going to go ahead and write this as p equals, the formula is L, the carrying capacity, so 3000 over 1 minus my c value. I'm going to skip c for a second, we're going to need to do some work for it, and then e to the negative 3, that's my growth constant, so 3, and t is the variable that I am going to keep inside the solution. So now I need to solve for that c, so let's remember the formula for c is the initial condition, so 50, minus L, so L is 3000 in this case, over the initial condition again, 50. So this is going to be pretty big. This is going to be negative 2950 over 50, which divides in evenly 59 times. So negative 59 is my value for C. So since this was minus a negative, it'll be plus 59 e to the negative 3t. So part A is solved. Using my initial condition, we wrote p as a function of t. So we could actually rewrite this as P of t if we wanted to, just so we can easily see this is a function of t. We plug in different times, and the output is how many people have the flu at that particular time, because dp dt is the rate at which the flu spreads, so P of t is how many people have the flu at a particular time. So for part B, find the size of the population when t equals 2 days. So the size of the population of people that have the flu when time is at 2 days. So since P is a function of t in days, I need only plug 2 into this P of t function we found in part A. So P of 2 is 3,000 over 1 plus 59 e to the negative 3t. Oh, I'm sorry, 3 times 2. Oops. Because we are substituting in 2 now. And this is approximately 2,617. And we'll go ahead and stop there. So we'll round. So we're talking about people here. So I'm going to round to the nearest person. So 2,617 people have the flu after 2 days have passed. So that's a pretty significant jump. On day 0, 50 people had the flu. By 2 days later, 2,617 people had the flu. And so now find the number of days that have passed. That is the wrong version of passed. So P-A-S-S-E-D, sorry. So find the number of days that have passed when the flu is spreading the fastest. So first of all, what we can find pretty easily is how many people had the flu when the flu is spreading the fastest. So for part C, before I answer part C, I'm going to answer a question that's related to C, which is how many people have the flu when the flu is spreading the fastest. So that's going to be half of the carrying capacity. So half of 3,000 is 1,500. So 1,500 people have the flu when the flu is spreading fastest. Now we're going to need that piece of information to find what we're actually being told to find, which is when does that happen. So remember that P of t was the number of people with the flu. So number of people with the flu, and t is in days. So I want to know the number of days that have passed when the flu is spreading the fastest. So I want to know on what day the 1,500 people, the population, when this flu is spreading the fastest, occurs. So in other words, I'm going to solve the equation 1,500 equals 3,000 over 1 plus 59 e to the negative 3t. So this is definitely not something we would solve by hand. We can graph each of these on our graphing calculator and find the points of intersection. So 1,500 we can enter as y1, and 3,000 we can enter as y2. So let's take a look at solving this part on the calculator. I've gone ahead and entered 1,500 as y1 and then my differential equation as y2. And before I even hit graph, I definitely know I'm going to need to change the viewing window. So the viewing window I chose, my x min I'm choosing 0, and my x max I'm choosing 10, and my y min I'm leaving at negative 10, but my y max is what's going to need to change drastically. I'm just going to go ahead and choose 5,000. So I know that 3,000 is going to be in the mix. I need to be bigger than that. I need to definitely be bigger than 1,500, which is what I'm graphing. And I'm going to make my y scale 500. So here's the graph. So here's my logistic differential equation solution, and then here's my 1,500 constant function. So I want to know where they intersect. So I know the y value where they intersect. That's 1,500. That's how many people have the flu when the flu is spreading the fastest. But I want that time. So it looks like it happens somewhere between 1 and 2. So we're going to go to second, calculate 5 for intersect. And I'm on the first curve near the point of intersection. So enter, second curve, enter, and then guess, we're going to hit enter. So there's my point of intersection, x equals 1.359. So that's my t value. So at 1.359 days, that's when the number of people, so let's write down that quantity. So 1.359, and my units there are in days. That's the number of days that have passed when the flu is spreading the fastest. So at 1.359 days, that's when just a whole lot of people are getting the flu, and it's spreading the fastest. So that rate of change is the steepest. That's that inflection point value, but this is the input of the inflection point value, and then 1500 is the output. Alright, this is the final question involving logistic differential equations, and it is different. So we have the population of Alaska from 1900 to 2000 can be modeled by the logistic equation P of T equals this ugly thing, right? So P is the population and T the years after 1900. So the biggest distinction here is that we were now given a P of T. So this represents the population at any time t, but it's not a differential equation. So this is not a rate. This tells us how many people were living in Alaska at a particular time in years after 1900, depending on what t we plug in. So for part A, what is the predicted population for Alaska in 2020? Of Alaska. So we're missing a word there. So what's the predicted population of Alaska in 2020? So all we're being asked to do is substitute in a value, a time, into this population function. So this population function is exact, or it's supposed to be, from between 1900 to 2000. So that's why they're using the word predicted for the population in 2020, because that's outside the domain values. But we can still substitute in 120. So for part A, in 2020, that's 120 years after 1990. So that's going to be the value we substitute into P of T. So P of 120 years is going to be my answer. So whenever I have a function as ugly as this, I'm going to go to my calculator and enter it in as y1, because I'm probably going to need to take a derivative or an integral of it, or plug something in like I am right now, and I don't want to enter it over and over again. Alright, so here's my calculator, and I went ahead and entered the function in already. And I want to substitute 120 into this function, so I'm going to go to vars, yvars for y1, and I want y1 of 120. And enter. So the predicted population of Alaska in 2020 is 781,217 or 218 people. We'll round to the nearest person. So 781, we'll say 218. Whoops, 781, 218 people. So that's the predicted population of Alaska in 2020. So now for part B, how fast was the population of Alaska changing in 1920, and then how about in 1940? So if I'm being asked how fast something is changing, I'm being asked for a rate. So I'm being asked to evaluate a derivative, so the derivative of P of T, at two different times. So T is the number of years after 1900, so I want the derivative, so P prime, at 20, and I want the derivative P prime at 40. Now, since we already have the function entered into our calculator, we can go to Math 8, and we want the derivative of the function y1, first at 20. So 1,678. And in this case, I will go ahead and go to the thousands place, so 1,678.078. 1,678.078 is the rate of change at 20, and then we can go ahead and do the same thing at 40. So I'll just go up and then change that value to a 4. So 4,127,794. So these are the two rates, how fast the population was changing in 1920 and in 1940. So the units of this would be in people per year. Now for part C, when was Alaska growing the fastest, and what was the population then? So this is my solution, and let's remember what solutions to logistic equations look like. They look like L over 1 minus CE to the negative KT. So L is that carrying capacity. So when was Alaska growing the fastest, and what was the population? Well, I'm growing the fastest at L over 2. So the population at that time was 895,598 over 2. So that is 447,799 people. So that is the population when Alaska is growing the fastest. And then what was the population, or sorry, when was Alaska growing the fastest? So I want to know that time. So this is going to be similar to the last problem. I need to set 447799 equal to P of t. I'm not even going to write the whole thing out again. And then I'm going to solve for t. So I'm going to do that on my graphing calculator. So I need to graph this function, which means I need to modify the window. And so I've already gone ahead and modified the window here. So I chose an x min of 0 and x max of 150. And my y max I had to choose pretty big. I have is 800,000. So let's see. So that's what this function currently looks like, but I didn't graph the other number yet. So the other number was 44779. Whoops, missed a 4. 447799. And I'm going to need to figure out where these two intersect. So second calc 5. And we'll find out when the population was growing the fastest. So at 82.765. So we'll round that to years. So we'll just say at 83 years. But we're going to need to adjust our answer. So at t equals 83 years past 1990. So that means the answer to part C is 1983. So that's when Alaska was growing the fastest, and the population was around 447,000, around 800 people. And then what information does the equation tell us about the population of Alaska in the long run? So for part D, sorry we're running out of space, but in the long run, so as time goes on, in other words, we're being asked to solve this setup. As time goes on, as t approaches infinity, what's happening to P of t? Well, for any logistic differential equation solution, we know that the answer to this limit at infinity is the carrying capacity. So 895, these are such big ugly numbers, I'm sorry. So 895,598 is what we know is the carrying capacity of the state of Alaska. So this many people is the carrying capacity of Alaska in the long run. So that's what that sentence translates to in the long run mathematically, is telling us to think about what happens as time goes to infinity.